stratified, and gradually reservoir pressure was dropping. So they decided to increase the driving force from reservoir to production unit. They decided to reduce separator pressure. And if you reduce separator pressure, obviously it will impact the pipeline pressure. So the pipeline pressure also drop. And because of stratified flow, they couldn't protect top of the pipeline because the corrosion inhibitor would not touch the top of the pipeline. And there was a risk of corrosion at the top of the pipeline. For that reason, they had monthly program to inject batch inhibitor by putting the required amount of inhibitor, corrosion inhibitor, between two peaks and running the two peaks in the pipeline. So the corrosion inhibitor will be in contact with the top of the pipeline. Now, this process was supposed to be every month, but it was very bad weather, so they couldn't do it for a month. And also the temperature of the sea was reduced by 2-3 degrees. And when they finally managed to run the inhibitor, the pigs, and they got a blockage. And they increased the pressure to 2000 psi, and they couldn't remove the blockage. And they came to us saying that the blockage is hydrate. And we did the calculation. We say it's not a hydrate unless, because you increase the pressure to 2000, you might have a Joule-Thomson effect. But have a look at the wax problem. And then they said that no, because we never had wax experience in our pig receivers, so we don't have any wax problem. So now we are trying to investigate that. The result was that the pipeline was blocked and loss of production for 5 months. And they had to replace part of the pipeline. Very expensive blockage.
Okay. Okay, so let's start off this one by making the composition of the oil. I have the composition here. I guess you're seeing that. So this is the composition of the oils. This is the PVT, actually, a single flash PVT data here. I have it. So for making the composition, I need to copy these components and mole fractions from the Excel file to Hydrafact. Let me close this, everything. And then, okay, so because it's another case, let me create another database. I'll say Bax problem in desktop. Okay, so this is a completely new database. We don't have any composition in it. So let me create this one. And then, so I have everything here. I just need the cross-section, properties. Okay. I need to add cross-section, C36 plus. Starting is 36, 8722, 11261. Let me double check. Okay, it's correct. And then the mole fraction is 0.26. 0.26. Add up to 99. It's fine. What should I call this fluid? Reservoir fluid. Okay. I call this reservoir fluid. Right. Okay, so everything is ready, and I press create. Because I want to perform hydrate calculations, I need to have water in the system. So I just need to add water to the reservoir fluid composition. So instead of creating another fluid, it's just easier to edit this fluid by adding water to it. I added water to the system, and then I just rename it to plus water, and then I press create new, and then I go to calculation tab, hydrate dissociation line. What are the limits from PSI to, okay. I change the units to PSIG from, I don't know, 500 to 8,000 PSIG by 100 steps. It's too much.
I mean, this next week is our last session of training, and basically we have a limitation on number of cases that we can disclose. So we are going to stop for 3 months and hopefully come back with some new case studies. If you have any case study that you can disclose and we can share with other audience, please contact us. So we need food for the feed or food for future training program.
Okay, I just changed the limit because 500 was above the minimum temperature. Okay, so this is bar, so I just need to change it to PSIG. Okay, so what I need to do is to add the operation conditions, which was 20 degrees, okay, which was 20.7 degree at 1200, and then 20.7 degrees at 400 because the pressure dropped, and then 18 and 400 bar. Okay, so see these points. This is the hydrate phase boundary of the system, and these points is the first operational condition at 20.7 degrees and 1200 PSIG, and then the pressure dropped to 400, and then the seabed temperature was decreased to 18 degrees. So at all these three operation conditions, we are outside of the hydrate phase boundary. So the blockage problem probably wasn't the hydrates. It actually, well, at least the calculation modeling shows that the problem wasn't hydrate, because at all these operation conditions, we were outside of the hydrate phase boundary.
Yeah, you see that even 2000, they put behind the pig. You see that is just about reaching hydrate phase boundary. So the only way hydrate can form is Joule-Thomson effect that can reduce the temperature of the system, assuming that one pig is blocked and we are forcing the fluid across that peg and cause Joule-Thomson effect. But that effect should disappear after a period of time, and hydrate should melt, and then we can should be able to flow the well, the pipeline. Also, we can detect if it is forming it is the gas what is coming out from the outlet of the pipeline. Is it due to hydrate dissociation or is it normal gas? We asked them to analyze the gas, and we were finally convinced that there is no hydrate because the gas released from hydrates are different from the gas which is flowing in the pipeline. So it was not hydrate. So looking at what is the other possible problem.
Okay. So now, when hydrate is off the table, so we have to calculate the VAX phase boundary of the system. So to perform a VAX calculation, first we need to characterize a fluid for VAX composition. To characterize a VAX characterization, you need to go to Fluid Management tab and then choose VAX characterization. A window will be open. Then you need to choose the reservoir fluid, which you added to the system, which is this one. And then just fill the information here. In this section, I will ask you about the VAX content because it's important, because we are actually extracting the alkanes which form VAX in the system. In the Hydrafact model, we assume that only alkanes, paraffins, they participate in the VAX phase. So we need to somehow extract the alkanes from other single carbon numbers, and then characterize them, and then tune the parameters, and after that perform VAX modeling. So this section asks for VAX content, which is important, and then you get to choose whether you want to tell the software how many pseudo components you need, but you can also ask if you want software to itself to tell you how many number of pseudo components is optimal. So I leave these two options in automatic, and then a new name of a fluid, because when you characterize a fluid, a new fluid is being created. So you just need to give the name for the new fluid. I just choose reservoir fluid underline VAX and CH, which shorts for VAX characterized. And then I just need to add this information. Let me go back to the Excel file. The GUR is 3070. Flash gas molecular weight is 25.22. Stabilized oil density is 0819. 0819. Stabilized oil molecular weight is 171.21. And I just need to add the composition of the flash gas and stabilized oil. I just copy these two columns because it's flash gas and flash oil. And then I right click on here and press save. Okay, that's it. So, and the VAX content was 4.37. 4.37. Okay, so VAX content is here. The number of pseudo components is obtained automatically. The GOR, flash gas molecular weight, every information, everything, the name has been chosen. So I just need to press characterize. So the characterized fluid composition is being shown here. As you can see, the alkanes has been separated from the SCNs. So SCNs were divided to F pseudo components and N pseudo components. So N is for paraffins and F is for other heavy cuts. This calculation is now ready. It's better to check if everything is okay. So looks everything's fine. So I add this to data. Okay. And then, so when the fluid was characterized, I need to tune it with experimental WDT data, which I have, and also saturation properties. So the bubble point I have is here is 5900 PSIG and 285 Fahrenheit. So I go to EOS tuning because I want to tune the model with saturation properties. I just change this one to PSIG and temperature to Fahrenheit. The pressure was 5900, temperature is 289, I guess. 5, and then I press tune the model. Okay, now the model has been tuned. It's always good to have a look at the results of the tuning. In the tuning, we correct the TC and PC and eccentric factors of normal alkanes, and so also the component study. And then it's really good if you look at this objective function here. It should be a very small number. As you can see, is the objective function, which is the deviation from this experimental data. The prediction from this experimental data is 0.003%, which is a very small number. It took 8 seconds to tune the model and also 21 iterations. Yeah, sure.
As Ramin mentioned, it is important to get bubble points right. The reason is that below bubble point, we have free gas. Now, when the pressure increases, more gas will dissolve in the oil or condensate. And that will reduce the concentration of waxy component. When the concentration of waxy component is reduced, wax appearance temperature or wax phase boundary move to the left because it's more difficult to form wax. So you need to cool down further. But then wax formation reduces the volume. Therefore, if we increase pressure, that will also reduce the volume. So there is two opposing factors. One is that as you increase pressure, more gas dissolves in the liquid, reducing waxy component concentration, and therefore pushing the wax phase boundary to the left. At the same time, when you increase pressure, you promote wax formation because both increasing pressure and wax formation are in the direction of reducing the volume. So these two forces are competing. For normal oil, black oil, the compressibility of oil is very low. So you see a complete change of angle on the black oil. You see that up to bubble point, the pressure of wax formation moves to the left, and then above bubble point, because if you increase pressure, there is no gas to dissolve. So increasing pressure shift the wax phase boundary to the right. But this is a volatile oil. Volatile oil is compressible. So you can see the wax phase boundary as you increase pressure, it moves to the left and then move to the right. So that is the reason we have this strange behavior on the wax behavior, wax phase boundary behavior.
Okay, thank you very much. Okay, so when the system was tuned, as I mentioned, just note this objective function. It should be a very small number. If it was a big number, that means that the tuning wasn't successful. So in this case, it's successful. So because every time you characterize a fluid, you create a new fluid which is characterized, and then when you tune it, then again you will create another fluid. So you need to choose another name. So this shows this name is reservoir fluid, wax characterized, then it was saturation tuned. So you can change this name, but I like just can change it to anything you want, but I just leave it as it is, and then you accept database, and then change it to bar. I just need to tune the wax model using WDT data. The WDT for this case was 42 degrees. And WDT is measured at atmospheric pressure. Yeah. So it's
Can I ask something about WDT?
Yeah, sure.
Yeah. For wax, we have two temperatures at any given pressure. We have wax appearance temperature and wax disappearance. As you know, each time that we are here, Ramin is showing the result of a QCM. You see that QCM, coarse crystal microbalance, the setup, one of the setup that we have here is a piezoelectric material. Its frequency, it has a resonant piezoelectric material. When you apply a voltage, like our course, like our watches, when you apply the voltage, it will resonate, and it has a, basically a frequency of resonate, and that frequency depends on the viscosity of the fluid, density of the fluid, and mass of the quartz. So you see that as we drop temperature, resonant frequency is reducing. And there is one point here that wax appearance temperature, that frequency drops sharply. This is the point that wax is forming and sticking to the quartz. So you see that sudden reduction in resonant frequency. Now, and then if you heat it, and you see that the wax deposited melt into fluid, and gradually the frequency goes back to original frequency. That point is wax disappearance. The beauty of QCM, coarse crystal microbalance, is that it can detect 1 nanogram, 10 to power minus 9. So it is very accurate with respect to detecting temperature. And as you know, when we are forming wax, we want to create a new phase. Creating a new phase means that you need to have some supersaturation. Like when you are forming hydrate, you need to cool down and go inside hydrate phase 1. When you want to form ice, ice doesn't form at 0. You have to go below 0. In fact, we say melting point, freezing point of ice. In fact, that's wrong. We have to say melting point of ice 0. So we need some degree of supersaturation. So this depends wax appearance temperature depend on how fast we cool the system, how much we mix the system, and other factors. But wax disappearance temperature is the real thermodynamic point. If you do it carefully and with a device that is very accurate, then you get the right number. Now, this real equilibrium point can be used in thermodynamic model, not wax appearance temperature, because it's not equilibrium point. Now, you might say, okay, why we design based on wax appearance temperature? We discuss it later. But for tuning the model, tuning the wax model, we need to use wax disappearance temperature. We can use wax appearance temperature, but the wax model is only good for that system, and it doesn't work anywhere else. So that's the reason that we need wax disappearance.
Okay. Thank you, Bahman. So as Bahman explained, the thermodynamic actually equilibrium for the onset of wax formation is WDT. So in order to tune the wax model, we always need WDT in Hydraflash. So if you don't have WDT, you can guess it from the VAT data you have, but still the only data we use for tuning the wax is WDT. So because WDT is measured at atmospheric pressure, I assume that it's atmospheric pressure and it's a dead oil. So so the pressure is 1 atmosphere and the WDT is 42. And then I need to choose that fluid which was wax characterized and also saturated with tuned with bubble point. So I need to choose that fluid. Otherwise, if I, for example, I choose this one and then Hydraflash gives me a warning. It says that the active composition has not been tuned with experimental saturation data. Please use saturation tuning model to tune the model with saturation data. Otherwise, the predicted wax phase boundary will not be representative of the actual fluid phase behavior of the system. Okay, so it says that would you like to continue waxing? I say no. So I choose this one, which was saturated, which was tuned with saturation properties, and then tune the model.
Obviously, wax disappearance temperature can be measured at atmospheric pressure or other pressure, depending on the setup you have. You know, with QCM, you can use at high pressure, but normally because industry uses other techniques like cross-polar microscopy and other techniques that normally does not work under pressure, a lot of wax disappearance temperature, if produced, are at atmospheric conditions.
So again, having a look at the objective function in the tuning, it's a very small number. So that means tuning was successful. And so I just choose a name. I let this name of the new fluid to be this one. And then I add it to it's being added to database. Now all the calculation is ready to perform using, you know, you can perform wax content or wax phase boundary calculation. I perform using the composition which was wax tuned. I perform the wax modeling, the wax phase boundary of the system. It's
obviously the model will produce wax disappearance temperature because
yes.
that equilibrium.
It's 100 points. So.
And then once we produce wax disappearance temperature, we can use the difference between wax appearance and wax disappearance and shift the wax disappearance temperature to the left, assuming that the system behaves the same. This is by prediction. Otherwise, we need to generate the data on wax appearance temperature versus pressure. But this prediction is good enough for the...
Okay. So this is the wax phase boundary of the system as wax is WDT at this range of pressure. But again, this is WDT. Let me add the point that the tuning point, which was 42 degrees and 1.05 bar. See, this is that actually shows that the tuning was the wax phase boundary represents the WDT very well. But yes, I can add the bubble point of the system from 5 degrees to 50 degrees. Okay, this is the bubble point of the system.
Yeah, you see that if you can magnify this section,
okay,
you see it's better. Yeah, you see that below bubble point, we have two phases. As you increase pressure, you get more gas dissolved in the condensate. So therefore, the concentration of waxy material is reduced. Hence, wax phase boundary shift to the left. But here, as I said, there is two opposing forces. One is the increased pressure promote wax formation, so shift the wax phase boundary to the right. The other one is that increasing pressure dissolve more gas in the liquid, shift the wax phase boundary to the left. And you see that because this is a compressible fluid, so here the wax phase boundary is shifting to the right. If it was a black oil, you would have seen something like this, moving here and then moving to the right. So if it was a black oil, because it's not very compressible, black oil is not very compressible, so it would have increasing pressure up to bubble point would have shift. We would have shifted the wax phase boundary to the left, and above bubble point, it would have moved to the right. Here you see that this is happening here. So this is the wax disappearance. We need now to add wax appearance and temperature to this figure.
Okay. So thank you, Bahman. Let me turn it to normal. So to get the VAT line, we don't have any option unless we translate the WDT line to VAT line. So if you go back to the course material and this data here, you see that we have the WDT temperature is 42, while the VAT is 21. So we have roughly 21 degrees of difference between WDT and VAT. So here what I can do is to just, deduct 21 degrees from the WDT line to get VAT line. So what I need to do is to extract this phase boundary to Excel. I just choose a path, desktop again. Okay. So now the data has been exported to Excel. So what I need to do is to deduct 21 degrees from the line, from the WDT line, which is here. Okay. and then add this to graph, to Hydrafact graph. So I just need a pressure here as well. So I copy this one, and then I go back to Hydrafact and add these points. Hydrafact is 100 points, so it's gonna, okay, good. Okay, so this is the as we can call it a VAT line. It's a 21 degrees difference between WDT line and VAT line. Do you want to add something?
Yeah, you see that you might ask, okay, if I'm operating here, so I am in the wax phase boundary, because this is thermodynamic wax phase boundary. Any point this side, lower temperature, can form wax. You are absolutely right. It can form wax. So we should design the system above wax disappearance temperature, as we do for hydrate. For hydrate, we can have a hydrate formation curve, and we can have hydrate dissociation curve. But we use hydrate dissociation curve as our design basis. Why don't we do it for wax? Because the wax formed from heavy components. As you know, there is normally an exponential decay in concentration of heavy components. So if you start from C8, C9 and plot concentration of heavy component, you see that there is exponential decay in concentration of heavy component. So first of all, it is difficult to form wax here in this region. If you form, the amount of wax will be very little. So we can put our design basis on wax formation. But for thermodynamic model, we need wax disappearance temperature. So for design, we can use this one, because the amount of wax, I think you have in calculation, right?
Sorry?
Showing that how much wax forms.
No, I haven't done that.
You haven't done it. Okay. We can calculate the amount of wax forming at this point if we assume all the waxy component can form wax at this point. Normally, it's very little. Yeah, maybe 0.5%, 1%. So very little amount of wax. But for hydrate form from light component, and you have plenty of light component in the system. So if you operate inside hydrate phase boundary, you can form a lot of hydrate. So that's why hydrate should be designed on the hydrate dissociation point, not hydrate formation point. You can consider hydrate formation line if you have some monitoring devices in the system. That if you are interested, we can discuss that risk-based hydrate prevention in this session or other session. We can discuss it. But for wax, we can afford designing on the wax formation temperature, but for hydrate, we have to be very careful.
Okay, thank you. Let's get back to the manual. Do you have any question up to this point? Okay. So this is basically this graph is the graph number 17 in the material. if you now put the operation conditions in the figure, you will see that the first operational conditions was outside of the wax phase boundary of the VAT line. And then when the pressure dropped to 400, it fell inside the wax stability zone. And then with further decreasing the system, it was completely inside. So that's why they had a blockage, because they had wax problem in the because with further decreasing the pressure, they were completely inside the VAT line. Yeah, sure.
The system, because of bad luck, you see that first of all, you reduce the system pressure, you move inside wax phase boundary, and then the weather is bad, you cannot run the pegs, and then the temperature drop. So all result in a wax problem when they run the pegs, and then they basically scrape wax from the wall of the pipeline, and then they get a blockage. The blockage, because it is a light oil, wax deposition in light oil is very dangerous, because the viscosity and diffusion, the viscosity is low, diffusion of waxy component is very high. So it is very dangerous to operate within the wax phase boundary for a light oil. For heavy oil, probably it won't block, but for light oil, can have a serious wax blockage.
Okay. So again, as you can see, we are inside the VAT line, so that's why they had a wax problem. But again, let's see, because as I was mentioning, there's difference between VAT and WDT. So let's calculate how much actually we will have wax if we're working between VAT and WDT line. To do that, you need to go to wax content calculation and perform wax content. Let me just remember how much, from 17 degrees, from 18 degrees to any temperature. So this is the wax precipitation line. I choose the line, and pressure, I choose how much was asked to, okay, 140.57, ESIG, 147, and from 18 degrees.
Yeah. Remember that this is a thermodynamic model. Assume infinite time for the system to reach equilibrium. Therefore, in reality, when you have wax appearance temperature, in this model, assume that wax formed from the minute you enter wax phase boundary. Yeah. But you see the amount of wax formed is between wax disappearance temperature and wax appearance temperature, the amount of wax formed is very little.
It's very little. So we get the same result, but let me talk on this one. So this is the WDT point, and this is the VAT point. And as you can see, the wax amount weight percent is 0.16%. So it's very, very low. So it means that below, between VAT and WDT, we have a very low wax content, and the amount of wax formed in the system is very low. So we won't have blockage problem. But when the system falls, behind the VAT line, because the wax content is no longer low, so we will have blockage problem. But as long as we are working between WDT and VAT, because in this case we have a very low wax amount, so this little amount of wax from the system doesn't cause blockage.
Yeah. But also we need to consider what technique is used for wax measurement, because if you are using differential scanning colorimetry, normally needs a lot of wax to form to detect it. So be careful what technique you are using for WAT. But because WAT depends on the device you are using. If you are using a device that needs a lot of, because differential scanning colorimetry, you need based on heat release on wax formation. So they need to cool down very fast and detect wax appearance temperature. Just be careful about the technique that you are using for a wax appearance temperature.
Okay. So if let's go back to the beginning of the case study. If you want to review what we have done, it was a pipeline. It was working at 1200 psig. Then the pressure dropped to 400 psig, and then the seabed temperature was reduced to 18 degrees. They had a blockage problem. They thought that it's a hydrate problem. Then we calculate the hydrate phase boundary. We realize that the operational conditions are outside of the hydrate stability zone, so the problem wasn't hydrate. Then we perform the wax modeling and we calculate the wax phase boundary of the system. It told us that, okay, this is the wax. We investigated the shape of this wax phase boundary. Bahman explained that. And then we translated the WDT line to VAT line, and we discussed the difference between VAT and WDT points. And then we put the operational conditions in the graph again. So we realized that actually in the third operational conditions, we are actually inside the VAT line, inside the wax appearance line. So the problem we are having is actually wax because we are inside that stability zone. And then we calculate the amount of wax we can form between WDT and WAT point. And then we worked out it was 0.14, the maximum is 0.16 weight%, which is a very small number. And then so we realized that working between WDT and VAT point, we have very low amount of wax formed in the system, and that low amount of wax doesn't really cause blockage. So
basically, in this case, the wax appearance temperature was mentioned in the PBT report, but basically after few years of production, no wax problem because they were operating outside wax phase boundary and they forgot about it. And when they reduced the pressure, the system moved into wax condition, and then they used the same pick to pick that doesn't have much tolerance, and therefore they collect the wax in front of it, and wax is very difficult problem to remove, especially for subsea pipelines, because you can't heat. Depressurization doesn't have any effect. Hydrate is much better. We don't have any line block with hydrate that has not been resolved. It can block the umbilical. There are umbilical block with hydrate, but pipelines we can resolve hydrate blockage. But wax can cause huge damage. Recently, it was a wax blockage in North Sea, costing around 100 million because you have to replace. So it is very, very risky, and we have to be careful.
Okay, so I think that we reached the end of this wax case study. Do you have any questions?
So maybe another 15 minutes.
Okay, so we will have another 15 minutes of break. and we will come back at 11:15 in UK time, which is in 15 minutes. And so we'll continue the asphalting modeling case study. Okay, so thank you.